Okay, welcome everyone to today's network seminar. And our speaker today is Markus Reineke, and he will tell us about quiver representations and neural networks. Please go ahead.
Thank you very much. Thanks a lot for the invitation and for the introduction. So this is about a joint paper with Marco Armenta, Thomas Brüskle, Sushila Yasun, which is already published in 2022. And the archive preprint, which you can see here, is even dating back to 21. So this project is somewhere around for quite a while. But actually, I haven't continued on this topic too much because I had no new idea. So let's see if the discussions after this talk somehow give some new impact into this project. So this is an application of quiver representations to neural networks, but on the other hand, it's also an application to quiver representations of neural networks. So neural networks, the concept of neural networks somehow inspired a new point of view on quiver representations, which I then elaborated. And the purpose of this talk is to, first of all, give to you a gentle, very, very gentle introduction into quiver representation, just using linear algebra terms and not using any homological algebra or algebraic geometry. So this will be definitely more than the first half of the talk. And then I will give you the main result, the main application of quiver representations. This will somehow look quite involved on the main result page, but then I will explain to you an example in all details, and we will see what this actually means. So, all right. So the plan of the talk is these 9 steps. So first, I will try to motivate quiver representations. Then I will define quiver representations, and then give you some sample results from the representation theory of quivers. Just 2 very specific sample results. There are, of course, many more, and I will maybe indicate some directions to you. And I will end this general introduction to quiver representations with the concept of moduli spaces, which is a concept from algebraic geometry, which is really essential to all this and to the way of thinking about this. And this is usually quite heavy stuff because you need algebraic geometry. I think I can get through just with linear algebra. And then we will start the application to neural networks by looking at an extreme toy version of neural network. It's a really extreme toy thing, as you will see. I will then model them by something called double frame quiver representations. And then I will show you the first main result, which we achieved in this paper. First in a qualitative version, which is easier to digest. Yes, please. Was there a question? No question. Okay. Show you a qualitative version, which is easier to digest, and then a quantitative version of the theorem, which I will then elaborate in an example. Okay, so that's the plan of the talk. So let's start with why quiver representations. So a quiver representation is just another language for a configuration of vector spaces and linear maps. And that's certainly a very, very general concept in all of mathematics, that you're looking at certain configurations of vector spaces and linear maps between them. And the representation theory of quivers, which emerged in the 1970s, addresses the classification problem for such configurations. Namely, you try to classify configurations of vector space and linear maps up to base change in all the vector spaces which are involved. I will make this precise on the next slide, but that's the basic idea. And to solve this classification problem, at least in some cases, you require some pretty advanced methods, namely methods from homological algebra and methods from algebraic geometry. And in the 2 sample results, I will show you the homological algebra methods, how they enter, and how algebraic geometry might enter into the picture. But you don't have to know about either algebraic theory for this talk. So that's the idea of the whole theory, of the representation theory of quivers, to solve these classification problems for configurations of vector spaces and linear maps, which are terribly hard in general. Okay, now to the what. What are quiver representations? So this is now basically a long definition. First is, what is a quiver? A quiver is nothing else than a finite-oriented graph. And our notation for this will always be the following. I will always denote the set of vertices of this graph by Q0, and I will assume it to be finite. And we will have arrows, which are always written as I arrow j, with the arrow itself is called alpha. And I and j are vertices. Yeah, so these are the edges of the graph, but they have a specific orientation. I will allow loops at a particular vertex. So an arrow might start and end in the same vertex. I also allow many parallel arrows between vertices. All this might happen, no problem at all. So this is, and the set of arrows is also finite. This is, in quiver representation theory, this is called a quiver. This is just a very poetic terminology. A quiver is something which is filled with arrows. That's why it is called a quiver. That's terminology due to Gabriel. Okay, so that's a quiver, finite-oriented graph. How do you represent a graph? You attach a vector space to each vertex and a linear map to each arrow. And this gives the following definition. A representation V of the quiver Q, say over the field of complex numbers, consists of finite dimensional vector spaces Vi for each vertex I of this oriented graph, and a linear map V alpha from the vector space Vi to Vj whenever you have an arrow alpha from I to j in our graph. Okay, so there are just two things to remark about this. First of all, the choice of the field of complex numbers as base field is absolutely unproblematic from the algebraic point of view, because complex numbers are algebraically closed. It might be a bit dubious from the network point of view, because you will certainly prefer the real numbers. Well, let's see. For the theorems which I will prove, complex numbers are basically essential. But of course, for everything, there are versions over the real numbers. But from the point of view of representation theory, complex numbers are much more natural. Let's keep this in mind maybe later for the discussion. Also note that the terminology is a bit unusual because every part of the representation should be called V. So V might have an index I for a vertex, then it's a vector space. But if you see V alpha, this is not at all a vector space. This is a linear map between the vector spaces Vi and Vj. The terminology is a bit unusual. You would usually call it phi alpha or F alpha or whatever. But here in this theory, it's V alpha. Okay, so representation of a quiver attaches a vector space to the vertex of the graph and to any arrow a linear map. That's nothing special. More special is the notion of equivalence. Two such representations, say V and W, are called equivalent if there exist isomorphisms of the underlying vector spaces, Vi to Wi, which intertwine the structure maps. And so this is the slogan, which intertwine the structure map, and then you can make this precise. This is the most important condition in quiver representation theory. So whenever you have an arrow alpha from I to j, you can do the following. You can first apply the structural map V alpha in the representation V, and then move to the vector space Wj, or you can, the other way around, first move to the vector space Wi, and then apply the structural map W8 alpha. And these two ways should be the same. That's the notion of equivalence. So equivalence means you have isomorphic vector spaces which intertwine the structure maps along the arrows. That's a natural notion of equivalence. And now the aim is classify all representations of Q up to equivalence. And this is for almost all quivers Q, this classification problem is completely unsolved. And many people say, not me, but many people say unsolvable. That's the surprising thing. We will see for which quivers it is solvable in a rather direct way. But let's first make all these linear algebra terms concrete, really concrete, and express everything in terms of matrices. So quiver representations as matrix problems. So to write everything as a matrix problem, I will first fix the dimension of the vector spaces in the quiver. So I fix a dimension vector. So in the following, if I have a boldface D, this always refers to a whole vector or a tuple of dimensions. Namely, this means that at the vertex I in the quiver, I have a di dimensional vector space. Okay, this I make concrete. If the vector space Vi, representing the vertex, is di dimensional, then I can just, without loss of generality, assume that this is just the standard vector space C to the di. So I implicitly fix a basis. Okay, the linear maps between these vector spaces are then just naturally represented by matrices. So the equivalence, the problem of equivalence of quiver representations can then be formulated as a problem of configurations of matrices. So classify tuples of matrices A alpha along the arrows. And for each arrow alpha from I to j, you have a dj cross di matrix. And you classify such tuples of matrices up to the following equivalence notion. You can replace A alpha by Gj A alpha Gi inverse if alpha is an arrow from I to j, where the Gi are certain invertible di by di matrices. Okay, so this is the very concrete and explicit problem. You're given a finite-oriented graph. You're given a vector of dimensions, and then please classify tuples of matrices along the arrows under this notion of similarity or congruence or equivalence, however you want to call it from your linear algebra. And I haven't made this explicit as an example, but let's just stick at an example and just ignore the whole graph structure and just look at a particular arrow. If you have just one matrix here along one arrow, then of course we can easily solve this classification problem. This equivalence notion then means you have a matrix and you are allowed to perform arbitrary row operations on the matrix. This is the multiplication by the left. And arbitrary column operations. This is the multiplication from the right. Well, and then we know from linear algebra, if we are allowed arbitrary row and column operations on a matrix, we can always bring this matrix to a normal form where you have almost all zeros and just entries 1 on the diagonal, and the number of ones is just the rank of the matrix. This would solve the classification problem for the graph, which is a single vector, which is a single arrow. But now the problem is you are given a very complicated configuration of arrows. And for example, imagine that you have many, many arrows, but only few vertices. Then it's immediately clear that this classification problem will be very complicated because you have only very few matrices Gi to transform your base change, but you have many, many matrices which you want to somehow bring to a normal form simultaneously. And that is somehow the interplay, which makes this problem very complicated in general. So for example, if you just have parallel arrows between two vertices, then you have a bunch of matrices which you want to classify up to row and column operations simultaneously. And that is a classical unsolved problem of linear algebra as soon as there are three matrices. Okay, so this is the Quiver representation. Usually in a longer lecture or longer course, I would now go through 3 or 4 separate examples to illustrate this matrix problem and to show you how complicated it is. But today I don't have time for this. So let me continue with how the Quiver representation theory emerges from here. Well, this basic linear algebra problem you can indeed study with tools of homological algebra, since the Quiver representations, which I introduced on the earlier slide, they naturally form an abelian category. And the structure of an abelian category is the natural playground for homological algebra. That's one approach. Another approach is that you can use tools of linear algebra, because what I just described here is a group action on a space. Namely, you have the group of tuples of invertible matrices acting on the space of rectangular matrices. And this is a reductive group action on an affine space. And that's where algebraic geometry has lots of things to say about. Okay, so this is why homological algebra and algebraic geometry somehow pop up naturally in solving such matrix problems. And they give kind of an algebraic conceptual Überbau to really study such very concrete problems. Okay, so that's the problem of Quiver representation theory. Now let me show you 2 sample results. The first sample result is somehow the starting point of this whole representation theory of quivers. This is Gabriel's theorem from 1972. This is somehow what started it all, and it gives a finite type classification. We will not use this theorem in the following, but it is such a classic that I just have to state it if I introduce Quiver representations. So the following 2 properties of a quiver are equivalent. The first property is Q is of finite type. That is, there are only finitely many equivalence classes of representations for every fixed dimension vector. So, of course, the number of equivalence classes of representations in all is infinite because, well, you have the different dimensions of the vector spaces involved. But once I fix the dimension of the vector spaces, it might happen that I have only finitely many equivalence classes. For example, the case of just a single matrix where you just have one invariant, namely the rank of the matrix. And this gives only finitely many equivalence classes. And this happens for Q if and only if Q is of the following shape. The non-oriented graph underlying Q is a disjoint union of the Dinkin diagrams of type A, D, E6, E7, E8. And this is the list of these diagrams. And this is a very surprising theorem. This is surprising because, well, first of all, it gives a complete classification of all these finite type quivers. Second, it proves that quiver representations somehow connect to many, many other areas of mathematics, because these Dinkin diagrams, they appear in many other areas of mathematics. They appear in root systems, reflection groups, finite dimensional complex Lie algebras. They even appear in mathematical physics, in conformal field theory, and so on and so on. So there are many, many places in mathematics where you have an ADE classification, and this is one more instance of such an ADE classification. So this shows quiver representations somehow connect to all sorts of mathematics. And so if you get interested in quiver representations and you want to run a reading seminar on that, usually in the course of one semester, you can really prove this first big structural theorem, Gabriel's theorem. This is typically for a third-year undergraduate reading seminar, you can reach this aim in one semester and do all the necessary homological algebra on the way. Yeah, so this is really a classic and well suited as an aim for first course on quiver representations.
So one quick question just before you move on. So
yes, please.
When you take the underlying graph, you forget the loops and the multiple edges, or no, you don't forget
there shouldn't be any loops or multiple edges. So okay. if I have multiple arrows from the beginning, they would survive in the underlying graph. So as soon as you have a loop or parallel arrows, you are actually out of finite type. Yes.
Okay. Thank you.
Yeah, you're welcome. Okay. Second sample result is more of the geometric nature. And for this, we need one more technical notion, namely the notion of an irreducible representation. So a representation of a quiver, so tuple of vector space and linear maps, is called irreducible if it has no proper compatible subspaces. That's the slogan. Let's make it precise. This means there are no tuples of subspaces ui and vi which are compatible with all the arrows, which means V alpha, the map, maps ui into uj for all arrows alpha from I to j in the quiver. That is a natural notion of compatible subspace. And V is called irreducible if it has no compatible subspaces, except for the trivial choice that all u are 0 or all ui are equal to vi. That, of course, always works. So now I have to warn you, this is something which you will only encounter in quivers where you have many, many oriented cycles, because if Q has no oriented cycles, then the only irreducible representations are one-dimensional representations, which means one of the vector spaces is one-dimensional, and that's it. And all the maps are 0. Yeah, so trivial concept. But now, the opposite case, if Q has many, many loops and cycles which you can wander around, then you might have such irreducible representations. And then this is even a generic phenomenon. So if for a certain dimension vector of a quiver D, you have one irreducible representation, then almost every representation is irreducible. And this almost every you can really understand, say, in a probabilistic sense. If you know that for a certain dimension vector you have one irreducible, then you can choose a quiver representation by randomly, and you have a 100% chance that it is irreducible. Yeah. So as soon as this property exists at all, it is a very generic property. But it only exists if your quiver has lots of oriented cycles. That's a strange concept. But why do I introduce this? Because there is a famous theorem of Le Brun and Procesi from 1990, which tell us that these irreducible quiver representations, these are the ones which you can always classify because you can distinguish them by functions. So that's the slogan. Equivalence classes of irreducible representations can be distinguished by trace functions, by so-called traces along oriented cycles. Okay, so here's the precise version of what this means. If you have two irreducible representations, V and W, first of all, the quiver has to contain enough cycles for these to exist. And if you have then two irreducible representations, then they are equivalent under this notion of equivalence, if and only if traces coincide. What does this mean? Well, you take an oriented cycle in your graph. So an oriented cycle means you start at a vertex I1 with an arrow alpha 1 and so on, IS with an arrow alpha S, and then you end up in I1. So you're going a full cycle. Now, if you have such a full cycle in your graph, then you can take the structural maps in the quiver representations, V alpha 1, V alpha S, and compose them, because you can compose along this path. And then what you get is a map from the vector space VI1 to VI1. So it's an endomorphism of a vector space, and an endomorphism has a trace. And you just take this innocent little number to trace. And these trace functions, they allow you to distinguish all the equivalence classes of irreducible representations. So if you take all these traces, then you know your irreducible representation up to equivalence. So these irreducible representations can be distinguished by functions. So they can, in principle, be classified. This is very nice. But only theoretically, because, well, this is nothing you can practically check, yeah, because there are infinitely many possible traces. But we can make this more concrete, and this will bring us to the concept of moduli spaces, yeah? So this concept of moduli spaces is a way to materialize this Lebrun-Purchesi theorem. So here's Lebrun.
Markus, could I interrupt with a question?
Yes, please.
So I know a little bit about quivers, but this theorem is new to me. So quivers of type AN, there's no cycles, and so the only irreducible ones are sort of these bars, the one-dimensional ones. Yeah. So if you instead have a quiver with one cycle, yeah, if you have a quiver with one vertex and one loop, yeah, then aren't the indecomposables sort of these Jordan blocks? Is that correct?
Yes, the indecomposables are the Jordan blocks, but the irreducibles are only those which are one-dimensional, where you have one everywhere.
I see.
Yeah, or just imagine instead of an oriented cycle, you just have a single loop and a single vertex.
Exactly, yeah.
Then you have Jordan blocks, but the only irreducibles are one-dimensionals, where you have a one-by-one block. And these you can then distinguish by traces, yes, which is quite obvious.
I see.
Yeah. So okay. Yeah. So in this situation, it's quite boring. So this is only interesting if you have many, many cycles. Like imagine you have such a full cycle, but you always have two parallel arrows.
Right.
And then you can have irreducible representations for large dimension vectors, and then you have many, many different ways to run around the cycles. And then this theorem is interesting. So right. It's very, very complementary to this Gabriel's theorem, which is about acyclic quivers. But this will play an important role in what I will do later. So this is why I have to state this.
Thanks. Okay. Appreciate it.
Okay, so let me now briefly explain the concept of modular spaces. Here's the Lebrun-Purchesi again. Equivalence classes of irreps are distinguished by traces along oriented cycles. Now, actually, for a fixed dimension vector, you only need finitely many trace functions to distinguish the irreducibles. This is a consequence of a very classical finite list result of Hilbert from his famous 1890 paper on finite generation of ideals in polynomial rings. And these finitely many trace functions you can use as coordinates for something called a space of equivalence classes of irreducible representations. And this is what people in algebraic geometry call a moduli space. Let me explain what we are doing. We run through all the irreducible representations. And for all these irreducible representations, we record these finitely many traces, these finitely many trace functions which distinguish them. And we record this as a tuple of points in C to the n. And the collections of all these coordinates which we get is called MD. And MD is then a space which classifies all the equivalence classes of irreducible representations for us. Yeah? So we materialized all the equivalence classes in a space by taking these coordinates. This is this concept. And actually, a theorem of algebraic geometry tells us this space MD is not something random, but it can be defined by polynomial non-equalities between these coordinates. So there are finitely many polynomials in variables x1 to xn, which define this space MD by saying these polynomials are 0 or non-zero. So this is a modular space. I would like to somehow appreciate this slide for 5 more minutes, but I'm running out of time somehow. So let me just say this is the way you materialize a space of equivalence classes. And now come to the applications to neural networks. So that was my very, very short introduction to Quiver representations. And now let's apply everything to neural networks. Okay, ready for the second part. A toy version of neural networks. So I fix vector spaces, which are different from the V, which I've already fixed. Those I have new name. U1 to UM and W1 to WN. These are new vector spaces independently from the Quiver representation. And a neural network is something which computes a network function, a function from the direct sum of the UI to the direct sum of the WI. And in our toy version, this network function will be a linear function because in the internal architecture, I will have no activation function. And now some of you might say, okay, I'm out. So this is too toy for me. If there are no activation functions, this is definitely not what neural networks are about. And you might be right, but everything I can do with this Quiver approach is linear functions. So in my approach, no activation functions are allowed. But I will show you in a few minutes why I still think that this is interesting. Okay, so this is the network. So we have some input states. These are vectors in these vector spaces U. And we get a certain output, namely vectors in the vector spaces W. And then there's a hidden part where some network function is computed. And now let me tell you what this hidden part is. This is an architecture of neurons. The hidden part is an architecture of neurons. And the neurons, for me, are just the following. Vector spaces Vj, where you have linear maps into the vector space and linear maps out of this vector space. And what this neuron does is just computing, again, a linear function. So here is what the neuron computes. The neuron takes vectors Vi1 to Vim at the inputs, applies all the linear maps F to them, and sums them up. This is this part. Sum over OK, Fk of Vik. It sums all of them up, and the sum of these input vectors is then distributed with these maps H to the output, to the Vk1. Oh, this should be a W. Wk1 to Wi1 to Win. Sorry, it's a misprint. Yeah, so you're just summing up all the input vectors after applying linear maps F, summing up and distributing this to the various outputs. And of course, the essential thing for you in neural networks is missing, namely to the sum you would first apply an activation function like ReLU. You would just take the maximum of this sum with a certain threshold value and then distribute the result. But this I'm completely ignoring because I just want to take a linear model of neural networks. Yeah, and it sounds boring, but there's still something going on. All right. So first of all, let's make the observation that what the single neuron computes is invariant under a certain base change action. Namely, I can multiply the F's from the left with G and the H's with G inverse from the right, and this doesn't change what the neuron computes. And this is the reason why everything can be modeled by quivers, because this way of computing something is compatible with the equivalence notion of quiver representations. Yeah. So, but again, I'm completely ignoring the activation function. It's not 100% correct. In this paper, there is a short section about how to bring ReLU activation into the game again in very special cases. But in first approximation, I will completely ignore it. My point of view is I just want to see what kind of network functions I can compute out of this linear architecture. So let me formulate this as the following aim. My aim is to define a moduli space encoding the internal states of the network up to base change. This is the concept. This is why I explained this concept of moduli space. And then I want to study the behavior of the network function along the moduli space. Yeah? So the moduli space should be a space in the sense of algebraic geometry, which encodes all the possible internal states up to this natural notion of base change. And knowing this moduli space, I will then want to know for which point in the moduli space do I get which network function. And this is what we will do using Quiver representations. All right. So here's what we do concretely. Double-framed representations. So this is a concept which didn't exist in Quiver representation theory. It is really inspired by this neural network point of view, this very, very simplified, simple-minded neural network point of view. So the neural networks really motivate to study so-called double-framed Quiver representations. And double-framed Quiver representation is a triple VFH, where V is a representation of a quiver, and that's the hidden internal architecture. That's the architecture of neurons. F is the input stage of the whole network. So these are maps from new vector spaces UI into the quiver representation. And H is the output stage, maps from the internal vector spaces of the quiver representation to the WI. So in this simplified model, the U and the W, this is what you see, and the internal architecture of neurons, this is hidden in the quiver representation somehow. So double-frame representation is such a triple. And for this, we have a natural extension of this notion of equivalence. Namely, I can transform VFH into an equivalent tuple by performing base change from the right and from the left on the quiver representation, like we did before. This is the notion of equivalence of quiver representations. And simultaneously transforming the input stage and the output stage. All right. So, and now I have a generalized version of this classification problem for quiver representations. Namely, instead of just parameterizing, trying to parameterize the quiver representations themselves, I now want to parameterize equivalence classes for quiver representations with a dedicated input and output stage under this notion of equivalence. And it turns out that this is really very orthogonal to Gabriel's theorem, where you have an ad hoc, where you have a finite type classification. You almost never have a finite type classification here. And so this is why you really will have to go into this algebraic geometry world of this Lebrun-Procesi theorem. And okay, so now I can already come to the main result. So here's the concrete classification problem. And now let me define a moduli space and say what I know about it. So for this, we need to know the dimension of the input stage, P, and of the output stage, Q. And we also have the dimension vector D of the internal quiver representation. We also need a notion of equivalence for such a double-framed representation. So here is this notion of equivalent of irreducibility, which I cannot motivate in a short amount of time. A double frame representation is irreducible if there is no proper sub-representation, such a configuration of compatible subspaces, containing the kernel of the H's or contained in the image of the F's. This is a technical notion. It just pops up from the general theory. Let's just take this for granted for a minute, and then we have the following theorem. We need a numerical assumption about the relation of the dimension vectors D, P, and Q. This is maybe not so easy to digest, but these are quite natural inequalities from the point of view of quiver representations. So under this numerical assumption, the equivalence classes of irreducible double-framed representations of this dimension type are indeed parameterized by a moduli space, a connected complex algebraic manifold MDPQ, which has this complex dimension. And if you look at this expression, then you will see that you can easily write down examples of dimension types DPQ, where these assumptions are fulfilled and where this dimension can be arbitrarily large. So you get moduli spaces of internal states of neural networks of arbitrarily large dimension easily with very, very small internal architecture. So even for, say, two-layer perceptron architecture, you can get even moduli spaces of arbitrarily high dimension. So this is the qualitative result. So this moduli space parameterizing the irreducible internal state exists. But now we want to know how it looks like. And this is now the next slide, which is a bit technical, but bear with me. I will give an example of what all this is. We want to now see the resulting network functions. So here's the qualitative. Let me show you the whole page and then try to digest this for a few minutes. So first of all, we need the notion of a path in a quiver. A path in the quiver, well, it's just a sequence of consecutive arrows. You start at a vertex I, which you call I1, pass with an arrow alpha1, and so on, alpha2, alpha S to vertex IS plus 1, which you call J. This is a path from I to J. Whenever you have such a path and a quiver representation, you have a map, V omega, from Vi to Vj, where you just take all the linear maps along the arrows and compose them. Yeah, fair enough. This we have implicitly already seen with these trace functions, where you have taken the path to be a full cycle. Okay, with this notion, I can now formulate a double-framed version of this Le Brun-Procesi theorem, saying that we can embed this space of states of the network into a very nice space, namely, well, I wrote this in very invariant algebraic way. This is a direct sum over all path of home spaces. This home space is just a space of matrices. So this here is a space of tuples of matrices. And into such a space of tuples of matrices, we can embed our moduli space of states in a very natural way. Namely, we take the function hj omega fi. The indices are a bit annoying, but what this is very basic. Well, you apply one of these input vectors, fi, from your input stage into the internal architecture. Then inside the internal architecture, you just take an arbitrary path. And at the end of the path, you take the output stage, hj. And then you have a map from the input stage to the output stage. And you collect all the possible ways to do this. And this gives an embedding of the moduli space. And under this embedding, one can really say what the network function then is, what the neural network computes. This is expressed in terms of certain components Q omega. And this Q omega, they have natural, I mean, we can even describe the image. The moduli space consists of those tuples of matrices. The Q omega are now just matrices in here, which fulfill certain rank conditions. Oh, so the details here are, there are lots and lots of indices. Everything is indexed by a certain path. This is not easy to digest, but I will show you in an example. But please just remember from this double-framed Le Brun-Procesi, which is our main result, the following. The moduli space of internal states you can write as a space of tuples of matrices. And the tuples of matrices which you get are defined by certain rank conditions. Yeah, that's the essence of this theorem. And now finally to an example. And that's then the end of the talk. So here's an example. Let's take the quiver 1, 2, 3, 4, 5. So there are 2 arrows pointing to 1 vertex. And then from this vertex, we branch to 4 and 5. And here are the dimension types which we considered. Well, the dimension type, the internal architecture is 1, 1, 1, 1, 1, which means I take one-dimensional vector spaces here, which is closer really to the neural network spirit. At the input stage, we have 2, 2, 0, 0, 1, which means you have a map from a 2-dimensional vector space to 1, from a 2-dimensional vector space to 2, and from a 1-dimensional vector space to 5. You will see the full picture on the next slide. And you have an output stage. You have a 2-dimensional output at 4 and at 5. So now I'll show you how the architecture...
So that's just the hidden part, yeah?
The D is the hidden part, and the P is the input stage, and the Q is the output stage.
Yeah, but the plot, the figure.
Exactly.
With one, okay.
The figure is the hidden part, and the full architecture in this case is the following. So here's the hidden part. And the hidden part is encoded by 4 scalars, A, B, C, and D. That's maps between one-dimensional vector spaces. Now, the input stage is phi, psi, these are linear maps from a 2-dimensional to a 1-dimensional space, and lambda, which is a scalar. And the output stage is 2 vectors V and W. So that's the full architecture here. Okay, now I can show you what this embedding of the moduli space looks like. Well, the moduli space embeds into homomorphisms from U1 plus U2 plus U5 to W4 plus W5, which is a space of 4 by 5 matrices. Aha. So this moduli space is sitting inside the 20-dimensional space of 4 by 5 matrices. And here's what you do. For example, what is this AC times V phi? This is the following path. You start here at the input, proceed with phi into the internal part. In the internal part, you go AC, and then you apply V, which is a vector. So you have AC times V phi. AC is a scalar, and V phi is a product of a vector with a covector, which is a rank 1 matrix, by the way. So you have 5 different choices of going from the input to the output stage, and these 5 choices you encode in this 4 by 5 matrix. And then the main result is we can say precisely which of these 4 by 5 matrices we get in the image. Namely, the moduli space is defined as the matrices A, B, 0, C, D, E. And I'm writing this E as lowercase because it is not a matrix, but a vector of length 2. The moduli space is 4 by 5 matrices of this form, such that the following 5 submatrices have rank equal to 1. AC should have rank 1. BD should have rank 1. The square ABCD should have rank 1. AB should have rank 1. And finally, the 2 by 5 matrix CDE should have rank 1. And that all these matrices have rank 1, that can be expressed in the non-vanishing of certain entries or in the vanishing of certain determinants. Yeah. So for example, this 2 by 2 matrix A has rank 1 if its determinant is vanishing. And these give you lots of polynomial equalities and non-equalities defining this moduli space precisely. So this is what you get in this particular example, which might not be too spectacular, but the results are at least very complete because we ignore all activation functions and we just keep the linear part of the story. So now I'm really out of time, and thank you very much for your attention.
All right, thank you so much. So maybe first we can unmute ourselves and give the Zoom applause to Markus. So
thank you very much.
Okay, do you have any questions?
I have a naive one because I don't work with Quiver. So the representation of the hidden part, is this just like 4 tuples of numbers of the irreducible ones of the we A, B, C, D? They're just like
exactly. The internal structure is just really 4 scalars, A, B, C, D. Yes.
I see.
So there is the notion of equivalence for this internal part is that you can perform a base change here in C, which means you can simultaneously, say at this C you have a scalar x, and you can multiply A and B with x and divide C and D by x. And this doesn't change the network function. This is this natural notion of equivalence. And then you might wonder, what are the functions which are invariant under this equivalences? And these are precisely, basically, these 5 functions which I wrote down here. And these 5 functions separate the equivalence classes. Yeah, so you can distinguish the internal part plus input plus output stage just by knowing these 5 values which are encoded in a 4 by 5 matrix. That's one of the parts of the theorem. Yeah.
Thank you. Thank you.
We have a Daniel who raised hand. Can you ask your question?
Yeah, of course. Thank you. Thank you very much for the presentation, Professor. I want to ask the same question that Tommy asked. Why do we need the inequalities on the qualitative theorem that you mentioned?
Yeah. Here we go. Sorry, what is the question? Yeah.
I think the question was, why do we need these inequalities, these assumptions?
These inequalities. Sorry. Okay. Yes. Now I get it. You need these inequalities because, I mean, there is a version of these theorems without these inequalities, but then you still have a moduli space parameterizing the irreducible double frame representations, but the dimension might be different. It might not be given by this rather simple formula. Yeah. So to keep the formula simple, you need this assumption, but there is a version of this theorem in more generality. Yeah.
Okay. Thank you, Professor. And another thing, what you call by irreducible is what Lebrun and Procesi called semi-simple representations. Is that it?
Simple, yeah. I mean, semi-simple is a direct sum of simples, and simple is equivalent to irreducible.
Okay. Yeah, makes sense.
So, I mean, the version which I showed here in this talk is, well, it's one of 4 theorems. And the first version is for just the irreducible representations. The second version is for the semi-simple representations, which is direct sum of irreducibles. Direct sum means you have somehow you can put your matrices into block forms and block diagonal form, and the blocks on the diagonal are irreducibles. Yeah, you can just pile them on top of each other. That is then a semi-simple representation. These can also be distinguished by the same functions, basically. I just wanted to keep the formulation of the theorem as short as possible. That's why I only work with irreducible. And there's not much difference because what I told you, if you have one irreducible representation, then almost all the representations are reducible anyway. So you are losing only a boundary phenomenon when you're not talking about, when you are only talking about irreducibles. And this is what I allow myself. Yeah. But there's a version for semi-simples. Yeah.
Thank you, Professor. And just one last question. I'm interested in how do you prove that that theorem? How do you prove that? What is the main argument for proving that it is a complex algebraic manifold? Do you use GIT or something like that?
I actually reduced this to the Lebrun-Procesi theorem because there is a process called deframing. And deframing means to replace your original quiver Q with this double framing datum by a new quiver. And this new quiver arises by, I really had to draw this, and I have no drawing tool attached to my computer at the moment. Okay, so let me see if I can show you this.
You can try to draw on Zoom.
I can just draw on Zoom, but yeah, okay.
If you're brave.
This would look really bad. Okay, so what you do the following. You basically take this diagram here, and now you contract all these vector spaces, U1, U2, U5, W4, W5. You contract these 5 to a single new vertex of the quiver. And then you have many, many arrows from this new vertex into the hidden stage and out of the hidden stage. So for example, you would say this U2 is 2-dimensional. So from this new vertex, from this contracted vertex, you have 2 arrows to here. And because of this 2-dimensional output stage, you have 2 arrows from here to this new vertex. Yeah? You have to contract input and output stage to a single vertex. And then you have many, many arrows from this vertex to the hidden stage and from the hidden stage to this vertex. And then I apply the original Lebrun-Procesi to this new deframed quiver. Because in this deframed quiver, I have many, many oriented cycles. And the trace functions for these many oriented cycles, these are precisely the functions which I wrote down here, these network functions. And in this way, I can somehow directly prove this from the Lebrun-Procesi for the deframed quiver. This is what we actually do in that paper. Yeah.
Okay, thank you very much.
So it's not really difficult. The proof is just 2 or 3 pages.
Thanks.
Okay, I see Tommy had a question in the chat about these inequality assumptions, but I think you already answered that. Okay, Tommy's yeah.
And not really necessary, yeah.
Yeah. And then Henry has a raised hand.
Yeah, you mentioned out loud that maybe under strict specific cases, there are versions of your theorem where you have ReLU activation functions. I was wondering if you could comment on that just a little bit.
Yes. So the restriction which we have to take is that then again we really have to assume that all the D's are one-dimensional, and sorry, let me go to the right page. Yeah, we have to assume that all the vector spaces VI in the internal architecture are one-dimensional, which is fine. We have ReLU activation, and the ReLU activation still, I mean, we don't get all the symmetries here. We don't get the full base change action, but we are still allowed to perform base change action with a positive scalar, with a positive, because that is, of course, respected by ReLU. And there is, in this particular case, there is a theory which gives you a moduli space, which is a theory in symplectic geometry. This is the so-called symplectic reduction. And when these moduli spaces of Quiver representations were invented in the early 90s by Alistair King, he also provided this symplectic reduction side of the story. And using this symplectic reduction from symplectic geometry, you can then produce a moduli space. You cannot produce it as an algebraic manifold, like in this linear setup, but only as a symplectic manifold, I think. Yeah, a symplectic manifold. And this you can define in this particular case. But it is very restricted, and I mean, I wrote some details in that paper about that, but I don't really see the applications, and I don't really see whether it is useful for the neural network point of view, I have to admit. Yeah. And it is also really restricted to ReLU activation. It doesn't work with anything else. So ReLU activation is still close to being, keeps the whole story close to linear because it is still piecewise linear. But if you have some other activation which really honestly destroys the linearity of the situation, then Quiver representations are out. Quiver representations just can't deal with proper non-linearities, I would say. I mean, I hope that someone proves me wrong. Yes. So if someone can manage to bring Quiver representations into this game in honestly non-linear activation, it would be really great. But I don't see a way to do this.
There was a question in the chat from Yaida. Do you want to speak out loud, or?
So let me see whether I can.
Or Yaida themselves, or you can. Markus also see it in the chat. So.
Yeah, okay. And now I can see it in the chat. Applying methods of algebraic geometry to the moduli space, sheaves, bundles, sections, or representations of a certain quiver tells us something about the quiver. Can we extract any information about it? Yes, I mean that is a big story which is really only developing in the last year. So, for example, if you have nice moduli spaces, then you might wonder, for example, what are simple bundles on them, like line bundles, and what are the sections of the line bundles, definitely. And there are by now a few theorems about that, but that's only beginning. And this is somehow, I wouldn't say it really tells you something about the quiver. It's really in the other direction. You really have to know the representation theory of the quiver in really, really lots of details to be able to say something about global sections of interesting line bundles on the moduli space. Yeah.
Okay. There was a raised hand from Rabia.
Okay, can we make double frame representation from everything? Yes, you can. Yes, so for example, you take any representation at this internal stage and just make a more or less random choice for the input and output stage. And then you have a 100% chance that you have an irreducible double framed representation. Yeah. So again, this irreducibility is a generic phenomenon. If there is just one possible choice, then almost any choice does it. And the only restriction is a certain numerical condition. This is the numerical condition between these dimension vectors D, P, and Q, which I wrote down. Let me come to this again. Yeah, these numerical assumptions just assure for you in a sufficient way that there exist irreducible double-framed representations at all. And then you can take any representation in the internal stage and just make a random choice for input and output stage, and then you have an irreducible representation. Oh, sorry, switch off the full screen mode. Yeah. Hope this helps.
I also saw Daniel raising hand. Daniel, you have a further question?
Yeah, of course. Yes, just the last one. So you mentioned that there was a problem with activation functions, even in the case of where we have thin quiver representations, right? That's the case when all have dimension one. I remember that there was a result from Jodoin and Armenta where they constructed a data representation and they mentioned that the network functions were always the same. Why does that not apply here? Or is there enough?
The reason is that yeah, I mean, as I explained, I somehow want to reduce everything to a situation where I can apply the original Le Brun-Procesi theorem. And this I can only do if there's no activation, if everything stays linear. So yes, there are approaches to circumvent this, but and there's something you can prove, but the results are not that complete. I mean, this result is rather complete in the sense that you can really describe what the moduli space is. You can really say you have this moduli space embedded into tuplets of matrices, and you can say 100% precisely what is the image defined by certain rank conditions. And you might have still qualitative results if you have activation, but they're not as complete as in this case. But well, I mean, yeah, it's just another direction. It's of course something one should do. Yes. Okay. And now I just see
Okay,
that.
thank you.
Yeah.
I think we are reaching the hour, so I will stop the recording now.
Okay.
But we can stay around and continue with further discussion and questions if someone wants. But I will stop the recording now. So thank you, Markus, for this wonderful talk.
Thank you very much for your attention.